Howdy, Aztecs! Welcome to Chapter 10, Part 2, Controlling Microbial Growth in the Body. So today we're going to look at the antimicrobial drugs that scientists have made, and then the mechanisms of action. So mechanisms of action is a really important concept. It just means how the drug works to control the growth of the bacteria or to kill the bacteria. Or I should say, kill the microbes of interest, because we're not only fighting a war against bacteria, we're fighting a war against viruses and protozoa and fungi, etc. All right, so let's check this cartoon out. Here's our microbe of interest. So in this case, it is a bacillus or a rod-shaped bacteria. Inside is the nucleic acid, so all this is nucleic acid. And then here, these are the ribosomes, so that's where you're doing protein synthesis. And then you have on the outside, you can't really see it in the cartoon, but on the most superficial aspect of the bacillus is the cell wall. And then deep to the cell wall is the plasma membrane, which is made of a... If you said phospholipid bilayer, you're right. So let's look at all these ways you could design a drug to destroy a bacteria in this case. You could inhibit the pathogen of interest, so that could be a virus or a bacteria. In this cartoon, it looks like this cartoon is a virus. So if you're designing a drug, you could inhibit the pathogen's attachment to or recognition of the host. So here, this is a virus, an envelope virus, and it's using proteins to recognize the host cell. So here's the host cell plasma membrane. You could design a drug, put a slashy through that would inhibit the attachment of the pathogen to the host. You could design a drug that would inhibit cell wall synthesis. So here's our peptidoglycan in our gram-positive cell wall. And if you inhibit the bacteria's ability to make this cell wall, then the bacteria can't survive. If you inhibit, so this part of the cartoon here, if you inhibit protein synthesis, bacteria can't make their proteins. Most enzymes they use in their biochemistry are made of proteins. So you can't make their enzymes, they can't do biochemistry, they can't do metabolism, and they're dead. You could also design a drug that disrupted the cytoplasmic membrane. So in this cartoon, you can see the phospholipid bilayer. So here's the hydrophilic heads and the hydrophobic tails of this layer. Here's the hydrophilic heads and the hydrophobic tails of the other layer. You could also, if you're designing a drug, you could also inhibit general metabolic pathways, and that's a little more complicated. You could also inhibit DNA synthesis. So when a bacteria divides, it duplicates its DNA so that the daughter cells can each have a set of chromosomes, or a single chromosome in the case of bacteria. But you could inhibit that. So then the bacteria itself may not die, but it can't make more of itself. So let's take a look at the bullet now. A good drug, good drugs versus bad drugs. A good drug is selectively toxic. That means that it's selectively toxic to the pathogen, but not to the host, which is us. So drug designers, legal drug designers, I should say, look for differences both in the structure and metabolism between the pathogen and the host. So as you know, bacterial cells are prokaryotic cells, and our cells, our host cells, they're eukaryotic cells. So legal drug designers look for ways to target prokaryotic cells specifically and not eukaryotic cells. So it's harder to design a drug against a fungi or a protozoa or a helminth because they're eukaryotes. We're eukaryotes. Fungi and protozoa and helminths, aka worms, are also eukaryotes. So you can't design a drug that destroys eukaryotic cells, because we all have those. It's really hard to design a drug for a virus like COVID, or aka coronavirus, because viruses come in and they utilize the host's metabolic machinery, so their enzymes and their ribosomes. So if you try to inhibit the virus once it's in our cells, that's difficult, could harm the host. And it's really important to know, I'll say it here, I'll probably say it several times, you should not and cannot use, well, some people do, but you should not use antibiotics on viruses, because antibiotics are designed to kill bacteria, not viruses. And when you use too many antibiotics, you probably already heard this, if you use too many antibiotics to kill things that aren't bacteria, then you build up resistant bacteria. They turn into superbugs and they don't respond to any of our drugs. Okay, so let's look at each one of these ways to design a drug in turn. So we said you could, if you're designing a legal drug, you could inhibit bacterial or fungal wall synthesis. So you could inhibit the fungal wall, even though a fungus is a eukaryote, it's got a cell wall. Our cells don't have cell walls. So, and we said this earlier, selective toxicity takes advantage of the structural or metabolic differences between the host, that's us, eukaryotes, and the microbe. Down here, for example, amoxicillin. So let's see if it's not on any of the lists over here, but a drug, maybe you've heard of it, amoxicillin, is very effective for treating infections caused by bacteria, but it rarely causes side effects in humans. Therefore, we would call amoxicillin selectively toxic. You could also, if you're designing a drug, you could inhibit protein synthesis. So that's this cartoon here. So here's the ribosome, here's the messenger RNA ribbon putting together amino acids to make a protein. That's protein synthesis. And that's when you take RNA, or specifically messenger RNA, and make that into a protein, that process is called translation. And so eukaryotic and prokaryotic ribosomes, so this pink thing, well, this thing right here that I'm circling, eukaryotic and prokaryotic ribosomes are different. So if you target the prokaryotic ribosomes, you, by definition, should not destroy our own eukaryotic ribosomes. You could inhibit general metabolic pathways not used by humans. And sulfonamide, maybe you've heard of that. That's a drug that inhibits a general metabolic pathway, but we've already gone over metabolism, so I'm not going to go into that. And the fifth way you could inhibit microbes is by inhibiting nucleic acid synthesis. So all these drugs will inhibit the microbe from making DNA or RNA, depends on the drug, and then they can't reproduce. You could also, number 6, block a pathogen's recognition of the host. So we talked about this cartoon. There's a virus trying to attach to the host. Oops, look at that. Number 3 came up last. That's funny. Oh well. You could disrupt the cytoplasmic membrane. So we talked about that. So the cytoplasmic membrane is here. Remember, it's a phospholipid bilayer. It's deep to the cell wall. And you should use a drug that disrupts the cytoplasmic membrane only externally on humans, because they can be toxic to human cytoplasmic membranes. And remember the cells on our skin, so if we applied the drug topically, cells on our skin are dead skin cells, so it's not going to hurt the host. That's us. So remember, if you inhibit the cell wall synthesis, so this is all peptidoglycans, it's big thick peptidoglycan with no outer membrane, so it's a gram-positive cell. Bacteria have peptidoglycan, we don't, so target the peptidoglycan in bacteria. So a common antibacterial drugs will inhibit that cross-linking between NAG and NAM chains in the peptidoglycan. We went over that at the beginning of class, talked about NAG and NAM in the that make up the kind of like the bricks in the peptidoglycan wall. There are, well, everyone's heard of penicillin, and maybe most people have heard of cephalosporin, but what they are is they're beta-lactam ring drugs, and they're most effective against gram-positive cells because they can attack the cell wall. Remember, gram-negative cells have this outer membrane, so superficial to the cell wall, that the drug can't get through the outer membrane to attack the peptidoglycan in gram-negative cells. If you design an antimicrobial drug that inhibits this cell wall synthesis, then the cells, the bacterial cells, will become more susceptible to osmotic pressure and they will lyse. So if they don't have the cell wall, they'll still have their plasma membranes, but water will rush into the cell, osmotically rush into the cells more easily without the cell wall, and the bacterial cells will burst. And here's a transmission, I think it's a transmission electron micrograph. So this bacterial cell was trying to divide, but it got probably a penicillin or a cephalosporin. It's gram-positive bacteria. And look, this is all the contents of the bacteria lysing out. So see you, bacteria. There's different kinds of penicillins, V and G, but natural penicillin can inhibit the cell wall synthesis. So penicillin is very important. Now you know how penicillin works. There's another drug, isoniazid, used to treat tuberculosis or TB. And what that drug does is attacks mycolic acids in the cell wall of Mycobacterium tuberculosis. So I don't know if you remember from the past, Mycobacterium tuberculosis has a specialized cell wall with mycolic acids in them, and isoniazid attacks those acids. You can use vancomycin for MRSA, for example. And then this bullet, drugs have no effect on dormant bacteria. Cells have to be growing, that means they're in the vegetative state, for the effect of the drug to take place. So if the bacteria is dormant or has formed an endospore, the drugs don't work. They have to be grown. The bacteria have to be growing. All right, so let's look at some more drugs. Bacitracin blocks the movement of peptidoglycan subunits. Those are the NAG and the NAM in the cell wall. Blocks the movement of those subunits from the cytoplasm to the exterior of the cell. So the bacteria could be making the peptidoglycan subunits here in the cytosol or cytoplasm, and then they ship them out to build the wall. And bacitracin blocks that movement of these subunits to the wall, so you can't build the wall. Sorry, bacitracin won't let you build the wall. Bacitracin inserts into the plasma membrane, so that's here, this is a plasma membrane made of a phospholipid bilayer, causes cell lysis. Bacitracin is natural, it's a natural drug, and it's topical, so you put it on your skin. If you're dealing with a fungal cell wall, echinocandins will inhibit glucan synthesis of the cell wall. And you can use this, echinocandins, to inhibit building of a cell wall in fungus. Protein synthesis. If you have a broad spectrum antibiotic, and a broad spectrum antibiotic just means it's an antibiotic that can kill many different types of microbes. Broad spectrum antibiotics usually act by inhibiting protein synthesis. All organisms that are alive on this planet use ribosomes, so these guys use ribosomes to make proteins. So if every living thing uses ribosomes, How can we use drugs that kill microbes by attacking ribosomes? Well, look what Mother Nature did for us. Prokaryotes have a 70S ribosome. And I know this math isn't right, but it is right. This is how they talk about the 70S ribosome. So the 70S ribosome has two parts, a 50S and a 30S, which should equal 80S, but it doesn't because there's some other cool biochemistry going on that I'm not going to talk about. Eukaryotes, on the other hand, have an 80S ribosome. Two parts, a 60S and a 40S. Should add up to 100, but it doesn't. It's complicated biochemistry. But eukaryotes have an 80S ribosome. So the legal drug designers have made drugs that attack the 70S ribosome in bacteria or in prokaryotes in general, and it doesn't hurt us too, but they're finding there are some side effects. Some drugs that target 70S may affect eukaryotes, but I'm sure that the scientists are working on that. This says tetracyclines block tRNA docking. So the transfer RNA just brings in the amino acid to the ribosome, and then the ribosome links up the amino acids to make a protein. Here's a cartoon of a prokaryotic ribosome. So here is the 50S subunit, and here's the 30S subunit. And then these are just pieces of RNA that are coming onto the ribosome. And then here's the eukaryotic ribosome made of a 60S subunit, this guy here, and a 40S subunit. And then we said this, prokaryotes have a 70S ribosome, eukaryotes have an 80S. More interesting drugs, aminoglycosides, that would include the drugs streptomycin and gentamicin, maybe you've heard of those, target the 30S ribosomal subunit. They change the shape of the ribosome, and then prokaryotic ribosome doesn't work. Tetracyclines are also protein synthesis inhibitors, so they can't make their proteins. Remember, if their enzymes are made of protein and you need enzymes to do biochemistry to live, then you're done. Here's some more drugs that inhibit protein synthesis. Chloramphenicol, maybe you've heard of that one. And then these are cool, antisense nucleic acids inhibit protein synthesis, so they inhibit RNA from going to the ribosome and making proteins. How about disrupting the cell membrane? So what you do is your drug that you're trying to use to disrupt the cytoplasmic or cell membrane, you incorporate that drug into the cell membrane. So where in the phospholipid bilayer you can put your drugs. For example, polyenes, those are antifungal drugs. Specifically, the drugs are nystatin and amphotericin B, attached to a component of fungal cell membranes called ergosterol. So fungus is a eukaryote, so it's got a phospholipid bilayer like our cells do. But then they also have this component that's in the phospholipid bilayer called ergosterol, and that's what the polyenes target. You could inhibit the synthesis of cell membranes, like azoles. Those are antifungals. They're harmless to humans, but they just prevent the synthesis of ergosterol that makes the fungal plasma membrane. If you inhibit ergosterol or synthesis of ergosterol, you can't make a functional phospholipid bilayer. Other drugs, polymyxin is effective against gram-negative bacteria such as Pseudomonas. It's natural, but it's toxic, so you use polymyxin topically. So this is a cartoon of the disruption of the cytoplasmic membrane of a fungal cell by amphotericin B. So here's a fungal phospholipid bilayer, just like we have. Here's ergosterol, this purple thing that we said fungal phospholipid bilayers have, but we don't have them. Here's the disruption of the membrane by amphotericin B. So the molecule, the drug, inserts itself in the phospholipid bilayer, and look, it's got like ergosterol, sort of a doorway here. These purple things are ergosterol, and then amphotericin can insert itself here and create a pore, and then once you have a pore into the cell, the cell can lyse, and then it dies. So this is inhibition of general metabolic pathways. So for example, you could design a drug, atovaquone, I think that's how you say it, that interfere with electron transport in protozoa. So remember the electron transport chain when we talked about metabolism? There's another drug, trimethoprim, interferes with making folic acid. Bacteria need folic acid to make nucleic acids. That's their DNA and their RNA. They can't make that. They can't make DNA and RNA. They can't survive. So let's check out this cartoon. So this big blue thing is an enzyme, and it's got an active site. That's where the molecule of interest binds to, which is the active site. And then at the top, it's got this para-aminobenzoic acid, and then the structural analogs, the sulfonamides, these guys up here, sulfanilamide, sulfamethoxazole, and sulfasoxazole. That was hard to say. Okay. Here's usually what was happening in bacteria. So the bacteria take substrates, use enzymes. They make dihydrofolic acid, have more enzymes, to make THF. Should be more enzymes here. But you can make these purine and pyrimidine nucleotides. That's A, T, C, and G, and U. And then from these nucleotides, you can make bacterial DNA and RNA. So, then in the cartoon, it's got PABA as a substrate and dihydrofolic acid coming off as a product. If you use, so this is a normal path, if you use these sulfa drugs, look what happens. So here's one of the sulfa drugs binding to the active site where PABA usually binds. So look at this. See this X here? That means PABA cannot bind to that active site. That means ultimately that bacteria cannot make DNA and RNA. So they can't make DNA and RNA, they can't survive. So let's check this guy out. Bacteria make folic acid, right? Which they then use to make nucleic acids. Yeah, we went over that. And we, humans, we get folic acid from our diet. We don't make it. And we use this molecule PABA differently. So it's not going to, if we give a sulfonamide drug, if that's in our body, and it won't inhibit this process we just talked about, because we don't do this process. We don't use PABA to make folic acids, then to make DNA and RNA. If there is a drug that's similar to PABA and it inhibits folic acid synthesis, any test question could be, it's most likely a sulfonamide aka a sulfa drug. Okay, different ways to inhibit metabolic pathways. You can inhibit viruses using amantadine. That prevents the uncoating of viruses. If the viruses can't take their coat off, then they can't replicate. You could also block replication of DNA or of DNA transcription into RNA with a drug in a bacteria. Those drugs include actinomycin and ciprofloxacin. These drugs are incorporated into DNA or RNA, and they prevent replication, transcription, or translation. There's a drug, rifampin. That's an anti-tuberculosis drug, and what it does, it inhibits RNA transcription. So you can't transcribe DNA into RNA. If you can't get RNA, you can't make a protein. And if one of those proteins is an enzyme, then you can't make the enzyme, you can't do the work in the cell, and you die. These are the nucleosides we were talking about, A, C, T, and G. Here's their structure. And then this just shows all the analogs of each one of these nucleosides, analog drugs that scientists are making. So for example, acyclovir. This could get incorporated in the bacterial DNA or RNA, and then you don't get, well, you prevent replication, transcription, or translation when you use these nucleoside analog drugs. AZT and valciclovir, they're antiviral nucleoside analogs that interfere with nucleic acid synthesis. So some antiviral drugs can interfere with nucleic acid synthesis. And remember, nucleic acids are RNA and DNA. Attachment, oh look at that, it's moving. The virus is getting in. It's pretty cool. Attachment of virus to the host can be prevented by peptide or sugar analogs of attachment or receptor proteins. So here's the attachment, or sorry, here's the receptor protein is on the plasma membrane of the host cell, and then the receptor proteins are here on the virus. So if you prevent the virus recognizing the host, then you prevent viral entry. Okay, AZT is a reverse transcriptase inhibitor, and that can be used to target HIV. So let's take a look at the cartoon. HIV is a retrovirus. So here's the virus, attaches to the host cell to be a helper T cell, and the virus is endocytosed into the helper T cell. The virus uncoats, and then you have free viral RNA in the cytoplasm. Then the viral reverse transcriptase reverse transcribes viral RNA into proviral DNA, which then inserts into the DNA of the host, and then you can start making viral, well, the virus will start making viral proteins, and then the viral proteins will assemble, the virus will bud off, and now you have a new virion. But AZT can inhibit this reverse transcriptase, and then the virus can't make more of itself. Tamiflu, maybe you've heard of that, is a neuraminidase inhibitor commonly used against influenza virus. So here's the host cell. Here's the budding virus. It's coming off the host cell. And here is a virion, so it's outside, so it's a virus that's outside the host cell, so it hasn't gained entry yet. This enzyme, neuraminidase, cleaves this receptor and then allows the, neuraminidase cleaves the receptor on the host cell and allows the virion to be released from the cell. If you inhibit that neuraminidase, then you inhibit the release of the viruses to the environment. And that's what it shows on the lower part of the cartoon. Neuraminidase inhibitors, no virion release. Clinical considerations in prescribing antimicrobial drugs. Ideal microbial. This is a dream list, so you can't really get all of them, but you try. So the ideal or dream list for an antimicrobial drug is that it would be readily available. It would be inexpensive, so everybody could get it. It would be chemically stable. You can store it for a long time. It's easy to administer, so maybe just a pill. It's non-toxic to humans. It's non-allergenic, so you don't form an allergy to it. It's selectively toxic against a wide range of pathogens, so you could use this drug to kill your pathogen of interest. But unfortunately, no antimicrobial has all these properties. So the clinician, when they decide which drug to give the patient, has to consider the range of pathogens against which the drug they want to give them are effective. So if a person has a gram-negative disease, then they have to give them, they have to know it's gram-negative, they have to know the type of bacteria and what drug will be efficacious against those bacteria, and also the drug dose. What's the difference between a poison and a medicine? The dose. And then how are you going to administer the drug and the side effects. And I said this earlier, it's inappropriate to prescribe antibacterial drugs to treat colds or flu because colds and flu are caused by viruses, not bacteria. And when you overprescribe antibacterial drugs, you're creating a super race of